Hello everyone, my name is Makumba Gerard of Ediman. In this video, we are going to use Newton-Raphson's method to come up with the formula that solves the functions which involve natural logarithms. After that, we shall draw the flowchart and run the flowchart. But hey, before we go in for it, if you are new here at Ediman, consider subscribing and hitting the notification bell such that you can be notified of the new videos that we make every day. So let us get started and see you there. Alright, using Newton-Raphson's method to come up with the formula which solves natural logarithmic functions. After that, we shall draw the flowchart and perform a dry run. We need to have a guiding example. So our guiding example is right here. Show that the iterative formula based on Newton-Raphson's method for finding the root of the equation, this here, is given by this. So we are going to use Newton-Raphson's formula first. You know that Newton-Raphson's formula xn plus 1 is equal to xn minus fxn divided by f derivative xn. Now, it is our task to find fxn and f derivative xn. So we shall have to select fx to be equal to 0 such that fx is equal to this function here because it is also equal to 0. So this is equal to 2 ln x minus x plus 1. So from here we can discretize this continuous function by bringing in or by evaluating it at a certain point of x. So we shall have fxn now becomes 2 ln xn minus xn plus 1. Next, we need to find f derivative of x. We differentiate this, not this. Reason being, this is a discretized function. In other words, it has been evaluated at a specific point, meaning it has become a constant. So we only differentiate continuous functions. So this here, when you differentiate this is going to give us 2 times differentiating a ln of x with respect to x. You will have to differentiate the function, which is 1 divided by the function itself. And this is x minus differentiate x with respect to x, you get 1. So f derivative of x is now equal to 2. I'm going to get the LCM there. 2 minus x all over LCM, and then f derivative of xn is equal to 2 minus xn divided by xn. Then we are going to bring the Newton-Raphson's formula and you substitute there. We shall have xn plus 1 equal to xn minus fxn, which is now 2 ln xn minus xn plus 1, everything over f derivative xn. So we shall have 2 minus xn divided by xn. So the next step is we are going to get the LCM. So from here, xn plus 1, this here is equal to xn into bracket, shall have 2 minus xn all over xn minus 2 ln xn, now plus xn minus 1, everything over 2 minus xn divided by xn. This here goes and we have xn plus 1 is equal to now 2 minus xn in the numerator, this and that go. So minus 2 ln xn plus xn minus 1 all over 2 minus xn divided by xn. xn plus 1 is now going to be equal to, let's call it like terms, this and that will vanish, this and that will have to reduce, and we shall have 1 minus 2 ln xn, everything divided by 2 minus xn all over xn. So this xn is going to go up, and we shall have xn plus 1 being equal to xn into bracket 1 minus 2 ln xn divided by 2 minus xn. So we need to check, is it what is required of us? So they have, this is 2 ln xn minus 1, then down here they have xn minus 2. We have the same, only that we need to multiply in the numerator and the denominator by -1, which doesn't change the equation. So xn plus 1 can be, by multiplying in the numerator and the denominator by -1, we shall have xn into bracket, this by -1 we have 2 ln xn minus 1, the denominator also by -1 we shall have xn minus 2. So we have come up with what they need, 0, 1, and they continue. Those are the values of small n. So we have finished showing that the iterative formula based on Newton-Raphson's method for finding the root of this equation is given by that. Part B, they need us to draw a flow chart which reads the initial approximation x naught of the root, Roman numeral 2, computes and reads the root to 2 decimal places. So that is what we are going to work on. Very important here to note, because this here makes us decide whether we should continue dry running or not. So what is going to be in our decision box is going to involve the maximum possible error, because 2 decimal places will have to give us that. So let us get started there. 2 decimal places imply that the maximum error is equal to 1/2 times 10 power -2, and this here is equal to 0.005, right? So we are going to start drawing our flow chart right here. Every flow chart starts with a start button. So our start button is right here. So we shall have to start the journey. So when you start, what happens next? We assign the values of smaller n. So next we are going to assign smaller n to be equal to the initial. You have to be aware of the symbols or the shapes that we use here. So the assignment shape is a rectangle, this here. So we are going to assign smaller n to be equal to 0. So let's see what the question demands of us. The flowchart that reads the initial value x naught. So we are also going to read x naught. Read is a command, okay? Read is a command, and therefore it should be represented in the parallelogram. So I'm going to bring here my parallelogram. So this here is where we're going to read the initial value x naught, right? Then let us see what happens next after we have read the value. Compute and print the root to the smaller places. Now the root can be computed using this formula here. So I'm going to bring in the box for computing or assigning. You know, that is supposed to be a rectangle. So within our rectangle, which is here, I'm going to print right there this formula, because we are going to compute basing on that formula. So everyone should note it down. So I'm going to have that formula coming in this box here. So I'll have xn plus 1 being equal to xn into bracket 2 ln xn minus 1 divided by xn minus 2, right? Now we have computed the xn plus 1. For this case, if n is equal to 0, we are going to compute x1, all right? Now, having computed x1 and we shall be reading x naught, that means before we continue, we have to calculate the error. So I'm going to bring in my decision box because it's the error that tells us whether to continue or we stop, right? So let me bring in my decision box. So our decision box is right there, and we are to use this decision box to decide whether we should continue or we stop. All right, so in the decision box, this is where we have the control statement is the error, which is xn plus 1 minus xn less than or equal to. We were given the maximum possible error. It's right here. We read the question and it required us to have our answer, to have this to 2 decimal places, which was interpreted by the maximum possible error as 0.05. all right, so is the error less than the maximum possible error, which is 0.005. It should be in equation form. So if the error is not less than the maximum possible error, so smaller n is going to become n plus 1. We shall add a 1 on the previous n. Consequently, even the values of x are going to change. So we shall have xn becoming xn plus 1. How about if we had the computed error being less than the maximum possible error, here being a yes? What would happen? Let's see what the question tells us. You only print or make a conclusion if at all the computed error is less than the maximum possible error. So right there we are going to print, and printing is a command. You remember that? So there we are now going to print xn plus 1, which will be the root of the equation, right? Now, having printed, what follows next is we shall stop. Stopping is always in the oval shape. So this here is our flowchart. We are going to the next part, that's part C, taking x naught, the initial approximation, to be 3.4. They need us to perform a dry run. All right, so I'm going to have my table here. X naught is equal to 3.4. So let us start. We shall start with the values of n, and n is assigned 0. Then we shall have xn plus 1. Then later on we shall check the error, which is xn plus 1 minus xn. Let's draw that table. So I've started with the x with the smaller n being equal to 0. I'm now moving. We started moving down. Smaller n is 0. It's here. Read the x naught. If you happen to put here smaller n, which is 0, we shall have x naught, and x naught is 3.4. Then we are moving downwards with our flow chart. We have to, when smaller n is 0, we are going to get here x1 being equal to x naught into bracket 2 ln x naught minus 1 all over x naught minus 2. So meaning that x naught is just coming here and shall be computing x1. So with our calculators ready, let us get started here. So when you compute on the calculator here, we shall have to get 3.5155. So we have x naught and we have x1. We need to compute the error, this minus that. The error is 0.1155. We left this box, we computed that. Now we are in this box. Is xn plus 1 minus xn less than 0.005? The answer is no. This value here is bigger than this. That means we have to dry run again. This previous n is going to be added by 1. So 0 plus 1 you get 1. And xn will now become, in other words, this value will shift here. Alright? So we have gone to n is equal to 1. So when you substitute here, we shall be computing x2, which is now going to be x1 Okay, but x1 is this value which is here. So let it come here, and we have 3.5155. Again, getting our calculator ready. We are going to feed in. We have reached here, and we are going to feed in this in the position of xn. So let's do that. Here we get 3.5129. Again, we get the error. We have finished computing here. Next, we have to get the error here. We have to get xn plus 1 minus xn. So this minus that, which is giving us 0.0026. When you check on this, the error here, we are still in the decision box, is the calculated value less than the maximum possible error. This here is 0.0026 and this here is 0.005. So when you compare the two values, this is less than 0.005. So it is yes. Yeah. They calculated the error, which is this, is less than 0.005. So that means we are going to print xn plus 1. So having discovered that this error is less than the maximum possible error, the question tells us to print xn plus 1. So what is it? 3.5129. And then we stop. But let's check the purpose of our question. So our question is right here. The purpose of our question is to find the root of the equation this. Alright, so the purpose is found in the first statement. So it computes, the flowchart computes and prints the root of this equation to how many decimal places? 2 decimal places. So that means we have to make that conclusion properly. So therefore, conclude and set the root to 2 ln x, that is the equation given to us, minus x plus 1 equal to 0 is, we write this to 2 decimal places, 3.512 decimal places. So next, before we end the session or before we end this video, I'm going to give you one question for trial. And our tryout question is right here. They need us to show that the iterative formula based on Newton-Raphson is the formula for finding the root of this equation. Then after that, we shall have to do the flow chart and we dry run. So that has been finding the roots of natural logarithmic equations using the flowchart. Once again, if you are new here at EduMath, consider subscribing and recommending to your friends such that they can as well receive these nice academic materials. So thank you very much and God bless you there.